Let's try to apply the fundamental property relationships in the Maxwell equations to an example problem. So this one deals with an 80-liter water heater that is sealed and full of water that is 130 Fahrenheit and 1 atmosphere. And say there's a safety hazard that breaks out, the temperature controller stops working. There's no room for the water to expand, and therefore if you start heating the water, the pressure is going to increase. And what we want to calculate is at what temperature will the pressure inside trigger the pressure relief valve. And say the pressure relief valve is designed to open at 10 atmospheres. We've got some other given information. We've got the isothermal compressibility, kappa sub T, is given there, and the coefficient of thermal expansion, alpha sub V, is also given there. So the first step in solving any problem, as always, is to draw yourself a process flow diagram. And this is a closed system, so I'm going to draw it in terms of my initial and final states. So initial state and final state. At this point, see if you can go through and put all the given information into these boxes for initial and final states. So here's that information. My pressure starts at 1 atmosphere and ends at 10 atmospheres. Volume stays constant at 80 liters the entire time. Temperature starts at 130 Fahrenheit, and temperature 2 is what we want to figure out. Now, maybe your diagram had some more information here, like maybe you chose to include the number of moles. That would be fine. You can include moles as well. Since it's a closed system, moles at 0.2 is equal to moles at 0.1. You may have also elected to include properties like enthalpy. So I could say H1 is equal to H2. In general, those will not be equal because we can guess that the temperature is going to increase and the pressure is going to increase. So enthalpy probably won't increase. You could also put entropy, any number of thermodynamic variables. The reason why I haven't included them here, or in the case of enthalpy specifically, is because it's not going to help us solve the problem. So you could put it there. It's not wrong to put it there. It just won't get you anywhere necessarily. Same thing for number of moles. I could calculate actually because I know what the density of water is, or I can look up the density of water to determine how many moles I have or how much mass I have. But the important thing is that the mass and the moles are staying constant because it's a closed system. And therefore, I said that V1 is equal to V2, and therefore V under bar 1 is also equal to V under bar 2. Okay, so where to start? Doing Gibbs phase rule is always a decent first thing to do. So I have to count the number of components and phases. Here I have one component, which is water, one phase, which is liquid, giving me a Gibbs phase rule equal to 2. That makes sense because we have pressure and volume specified in both cases, and therefore all 6 other thermodynamic variables are also specified. It's more appropriate to say pressure and specific volume, or molar volume, are known in cases 1 and 2. Also note that I could have calculated what the specific molar volume was. I elected not to because it ends up not mattering in this case, and we'll see why in a second. So now, again, what we want to do is relate what we know to what we don't know. Okay, so in this problem, what is known? We've got 2 known variables. We've got P that's known and V under bar that's known to what we seek to know. T is what we want to know. We want to know what the temperature is at 0.2. So therefore, I can express T as a function of any 2 other variables. And in this case, I want to express T as a function of V under bar and P. All right, so next I'm going to write a mathematical expression that is going to relate the change in T to the change in the other 2 variables. Whoops. Okay, sorry about that. I accidentally closed my OneNote. So I want to express the change in my dependent variable, which is T, to changes in independent variables. So again, that is dt is equal to the partial of T with respect to one variable. So partial with respect to volume at constant pressure times the change in specific volume, plus the partial with respect to P at constant volume times the change in pressure. And because the problem states that volume is staying the same, my dV term is 0. So dV is equal to 0 since volume is constant, or specific volume is constant more specifically. Okay, so that term can go away, and I'm left with dt is equal to partial of t with respect to p at constant v. So we do have constant v times the change in pressure. Now at this point, do not say, well, I know what t is. So you may see dt dp at constant v and say, oh, well, I can measure all three of those variables. So you may be tempted to say by the ideal gas law that T is equal to PV over R by ideal gas law. This would be incorrect to say this. So think to yourself, why would that be incorrect? And the answer is that for an ideal gas, the ideal gas law applies, but we have a liquid here, so we can't use the ideal or any equation of state for a gas. Now, it is true that if we did know what the equation of state was, so some equations of state that we'll cover later this week in our review of thermo, if I knew what that equation of state was and it was valid for the gas as well as the liquid, then I could use that equation of state. However, the problem doesn't tell me to assume any equation of state, and furthermore, it gives me information relating to the isothermal compressibility and the coefficient of thermal expansion. So if the problem didn't say this is your given information, you could assume an equation of state like Peng-Robinson or Suave-Redlich-Kwong would be another one that would be valid for the liquid as well. You could theoretically assume that equation of state and solve for t and then take the partial of that expression with respect to p at constant v in order to solve the problem. Right, so also as an aside note, I said earlier that you should always use data if it's available. So solving this problem with the steam tables is also a perfectly valid approach to solving this problem. But this problem is supposed to be just an illustration of how you would use the stuff that we've gone through in the last couple of videos. Whereas if this were actually a homework problem, I think that the steam tables would be the best way to go about solving it. So we're pretending for just sake of argument that we don't have a steam table, and instead we only have the isothermal compressibility and the coefficient of thermal expansion. Which, by the way, I have to give you what those terms are. These are well-defined terms. This is kind of like heat capacity, where it's just something that you would look up, and it's defined on a certain basis. And again, you may have seen these in thermo class. But alpha is the coefficient of thermal expansion. That is equal to 1 over the specific volume, specific molar volume, times the partial of V with respect to T at constant P. So this is coefficient of thermal expansion. And you can remember it by relating the name. So thermal expansion. So thermal means that it happens as a result of changing temperature. So that's one of the independent variables. And expansion implies that something is expanding or its specific volume is increasing. So this literally measures the increase of volume upon an increase in temperature, or the other way around, the decrease in volumes, in molar volume on a decrease of temperature. Kappa T is the isothermal compressibility. That is defined as 1 over V, negative 1 over V, times the partial of V with respect to P at constant T. So this is isothermal compressibility. And isothermal here implies that T is constant, as written in the equation. And compressibility means that it measures how much pressure can increase what the volume is. So for a liquid, oftentimes when we say it's incompressible, we say the isothermal compressibility is 0 because the molar volume doesn't depend on pressure at all. So that's kind of like another, it's an analogy to the ideal gas law where Gibbs phase rule doesn't apply to an isothermal gas, Gibbs phase rule doesn't apply to a incompressible liquid. That's what I was trying to say. But not all liquids can be treated as incompressible. So oftentimes they will have very small isothermal compressibilities, and in this case we have an actual value for what it's supposed to be. So notice that both of these terms involve the same three variables, so V, T, and P, and it also matches the same three variables we have from the DT expression. So if you look at what we've got TPV, VTP, and VPT. So right away, that kind of triggers a thought of maybe the triple product rule can be used in this problem. So use that mnemonic for the triple product rule where you just write the partial of one variable with respect to another at the constant third variable. And then just rotate the three variables on the left-hand side and set those equal to -1. Then remember that we want to calculate what dt dp at constant v is. So we want to take the other two over to the other side. So we've got minus, and then dp dv at constant t, and dv dt at constant p. Notice that dv dt at constant p, we can rewrite that as the coefficient of thermal expansion times the specific volume. So this is equal to V times alpha. And then we can use the reciprocal rule to get this other term, this dp dv at constant t, up to the top and also flipped. So we can say this is equal to dv dp at constant t over v times alpha. And then we can say that this dv dp term is equal to minus v kappa. So minus v kappa over v alpha. Those will cancel, and we are left with simply dt dp at constant v is equal to the ratio of the isothermal compressibility over the coefficient of thermal expansion. So plugging back into my equation above, where I say that dt is equal to, that partial derivative is minus kappa over alpha times dp. I get that right? Yes, I got that right above. All right, so now we can simply integrate both sides. And we're going to integrate from T1 to T2 and P1 to P2. All right, so T1 was 130 to T2 of dt is equal to, now kappa and alpha are both constant in this case, right? So that can come outside of the integral. And we're going to integrate dp from 1 atmosphere to 10 atmospheres. You should always double check that your units are canceling. So kappa is given in terms of, let's see, where did I give it? Kappa is given in terms of 1 over atmosphere, and alpha is given in 1 over degrees Fahrenheit. So thankfully, those are consistent with the units of our problem. All right, so units are going to check out. So I have two really simple integrals here. I don't have any functions inside, so I simply get T2 minus 130F is equal to, see what my values were for kappa, was 4.5 times 10 to the negative 5, 1 over atmospheres, over alpha, which is 2.90 times 10 to the 4 degrees Fahrenheit, and P1 minus P2 is 10 atmospheres minus 1 atmosphere. And then turning to the calculator, you can solve for T2. In this case, your answer is T2 is 131.4 degrees Fahrenheit, which is very surprising. Remember, we started at 130 Fahrenheit and 1 atmosphere. And just by heating that temperature by 1.4 degrees Fahrenheit, we've increased the pressure up to 10 atmospheres. So this problem illustrates why you oftentimes hear in chemistry classes to never heat a closed vessel, especially one that has no headspace, because your pressure can build very, very rapidly. All right, that was all for this example.